So as we mentioned, okay, from tables, since we know P1, T1, we can get the value of H1 and S1. Why we need to find S1? Because for the isentropic case, S to S will be equal to S1. Once we find S to S, and we know at state 2 the pressure P2, having two properties, P2 and S2 for isentropic case, we go to the tables and we get H to S. And then all we have to do is to replace H1 and H2S in the formula since W dot over M dot real is given. So we find that the isentropic efficiency for this turbine is 75%. Sometimes they do it in another way. They give you the isentropic efficiency and you should solve for the actual work. Okay, so just you need to understand the formula, and depending on what is given, you decide how to find your unknowns. Now, if we take the compressor, it's very similar to the turbine. We can start first by writing the energy balance, which is very similar to the one of the turbine. But here we put work on the system, so W dot is negative. So minus W dot control volume over M dot is H2 over H1. Please remember, always start by the big formula and simplify, because sometimes if they give you velocities, this equation will be different, okay? Or if you have change in potential energy, you should account for it. So always do the general balance and then simplify terms. Now, similarly, if we take the entropy balance, because we consider in a diabatic process, also here Q dot will cancel out. So we can write, as we did for the turbine, that sigma dot production over M dot is S2 minus S1. So also here, it's impossible to have S2 smaller than S1. And if we do the interpretation on the graph H function of S, in the pump, we do the opposite of the turbine. We increase the pressure and H will increase. And if it's a reversible process, S1 should be equal to S2. So S2S will always present the point 2 when you have isentropic case. While in real scenarios, we always have some irreversibilities. This is why S2 will be larger than S2S, because as we demonstrated together, sigma cannot be negative, so it's impossible to have S2 from this side. It's wrong. It should be from the upper side. And because of this, if you observe your graph, you know that the ideal work that you put on the system, okay, is just H1, the difference between H2S and H1. So this is the input work that you should put if you have isentropic case. While in reality, you will put more work. You will put more work to your compressor to perform the task because of irreversibility. And this additional work will be due to the fact that delta H for the case of a pump, okay, or compressor, will be larger than H2S. Yeah, just 1 second. Okay, will be larger than H2S minus H1. So for the case of the pump, how we define the isentropic efficiency for the case of a compressor or pump? For a case of compressor or pump, we define it in the opposite way. Okay, and instead of doing H2 minus H1 over H2S minus H1, we do it in the opposite way. Why? Because for the compressor and pumps, H2S minus H1 will be smaller than H2 minus H1, because for the ideal case, we'll put less work to operate the system. Okay, so keep in mind, with turbine, it's a work output. So the actual output is smaller than the real the ideal output. Okay, بينما بالpump we put work on the system, we put work. يعني بالايديال scenario will put less than بالirreversible case. Okay, so for the efficiency of a compressor or pump, it's computed in the opposite way. It's delta H isentropic over delta H real. Now, what about isentropic nozzle efficiency? Okay, let me remind you of the equation for a nozzle. if you remember, whenever we have a nozzle or diffuser, okay, we don't have Q dot, we don't have W dot, we just have variation of the velocity. So we can use, if you remember the diffuser, in the diffuser we have increased area, so this will reduce the velocity, while in the nozzle it's the opposite. We reduce the area to increase the velocity, okay? But in both scenarios, if you remember from chapter 4, what is the equation if we take the energy balance? If we take the energy balance, you have, you can start from the general one, 0 equals, for steady state, of course, you have Q dot minus W dot plus M dot. Since we have one inlet, one outlet, M dot in equal M dot out. So plus M dot times H1 minus H2 plus V1 square over 2 minus V2 square over 2 plus the variation in potential energy. So plus G Z1 minus Z2. هلا انه in general we neglect variation of potential energy, but of course for a nozzle we cannot neglect variation in kinetic energy, okay? Because we have variation of velocity between 1 and 2. So this term will cancel out, and the purpose of the nozzle will be to increase the velocity at the outlet. So we have a difference between V1 and V2. How to find this difference? Of course, they will give us information. You know that M dot N, if you remember, M dot N is equal to M dot out. And how we calculate M dot? M dot is AV over specific volume. So you can relate the inlet and outlet state to get the value of V2. Okay, so here you can, from P1, T1, you can determine the specific volume V1. From P2, T2, you can determine the specific volume V2. So you can find accordingly, depending on the areas given, how the velocity will change. Okay, now, what about isentropic efficiency of a nozzle? You know that the nozzle will increase the velocity, but if we have irreversibilities, we'll have some losses. This is why we can compute, for the case of a real case, we can calculate what is V2 square over 2. And in isentropic case, so if S1 equal S2, what will be V2 square over 2S? And then we do the ratio. Of course, V2 will be smaller than V2S, because whenever you have irreversibilities, you lose, you have, like, if you want, production of entropy, and this will lead to a reduction of the efficiency of nozzle. So in case you have in a problem to calculate, for example, the velocity, and they give you what is the isentropic efficiency, you can just get what is V2S from isentropic efficiency, because in case of V2S, what do you have? You can say directly S1 equal S2. And this will help you when you put S1 equal S2, you can know more about state 2. You can, for example, if they don't give you T2, they just give you P2, okay? For isentropic case, P2 and S2 will give you T2S. And if you have the actual value T2, you can compare the two cases. And you can apply the energy equation for case of T2, what is the velocity I have? And for the case of T2S, what is the velocity I will get? And then you can compute then what will be the efficiency, isentropic efficiency of your nozzle. Or it can be in the opposite way. They give you the efficiency, you calculate V2S, and then you deduce the value of V2. Okay. Let us take an example to practice more on how to use the efficiencies, the isentropic efficiencies. We have the following figure. In the following figure, a steam turbine have an isentropic efficiency of 90% and drives an air compressor having an isentropic compressor efficiency of 85%. Steady state operating data are provided on the figure. Assume the ideal gas model for air and ignore stray heat transfer and kinetic and potential energy effects. Determine the mass flow rate of the steam entering the turbine in kilogram of steam per kilogram of air exiting the compressor. And repeat part A if you have that the turbine efficiency is equal to the compressor efficiency equal to 100%. So to start with, they gave us a real case where we have irreversibilities. And we know what is the isentropic efficiency of the turbine. And we know the value of the isentropic efficiency of the compressor. Okay? So this will help us into finding our unknowns. First, what do we want to find? We want to find the ratio of the mass flow rates. So we need the ratio between m dot steam over m dot air. This is the purpose. Okay, so always, as we mentioned before, keep in mind to use both the energy equation and the second law of thermodynamics. Okay, to start with, let us look at the figure to see what are the components that we have. We have in this problem, okay, a turbine driving a compressor. Okay, and sometimes the same turbine can drive several parts. In some cases, let's say in cars, for example, they can tell you we have a turbine, it will drive the compressor, and also it will drive, let's say, the dynamo. Okay, you have to produce electricity in order to operate your car. So in this case, the turbine work can be divided into work provided to the compressor and work provided to the generator. But here in this problem, we just have a turbine and a compressor. This means that all work produced by the turbine will be used to drive the compressor. Okay, it's not, you don't have any other part. And the turbine is just here to drive the compressor. So we can say that W turbine out will be equal to W compressor in. Okay, and this is why it's a good strategy to take the whole system as system. Why? Because if we take it as a whole, هيدا exchange بيصير internal. Since what is getting out from the turbine is getting into the compressor, we don't have any other, if you want, other device driven by the turbine. If you have any other device driven by the turbine, you should add the work delivered by the turbine, which is not the case here. You just have exchange between the turbine and compressor. So you can take the whole system and say, if I take this whole system and write the energy balance, what is the energy balance? Q dot minus W dot for my control volume plus sum m dot n Hn minus sum m dot out H out equals to 0. Okay, and in this particular case, first, no heat transfer because turbine and compressor can be considered as adiabatic devices if they don't mention anything in the problem. This term will cancel out. The exchange of work is internal to the system because everything provided by the turbine is taken by the compressor. This term will cancel out. So we just have then sum of m dot n Hn equals to sum of m dot out H out. Okay, now what do we know in this problem? Okay, we want to get the ratio of m dot. So we can write that if we apply this equation, we have the following. We have m dot air. For air, what do we have? We have one inlet, one outlet. Okay, you have air is entering at state 3. So I do m dot air times H3 minus H4. Is equal, or you can add plus m dot steam. For steam, inlet is 1 and outlet is 2. M dot steam H1 minus H2 is equal to 0. And since you need to determine the ratio, okay, so you can say that m dot steam over m dot air is equal to the following. So if we take this term m dot air to the other side, okay, what do we get? We get H3 minus H4 over H2 minus H1 لأنه هي أخذتها لتاني يلي بتصير H2 minus H1. So it's H3 minus H4 over H2 minus H1. I should determine my enthalpies in order to come up with the ratio of m dot. To start with, okay, what do I know in this problem? For steam, I know P1 and T1. So what can I do? I go to the tables and I get H1. Okay, but since I don't know, I know only P2 for the outlet state, I cannot find H2. I need another information. This is why they gave me the isentropic efficiency of the turbine. Because they gave me the isentropic efficiency, what can I write? I write the isentropic efficiency of the turbine is equal to H1 minus H2 over H1 minus H2 isentropic, H2S. Okay, so I can say that I can replace then H1 minus H2 by what? By the isentropic efficiency of the turbine times H1 minus H2S. I already have H1, I just need H2S. How to find H2S? I know that for isentropic case, you need to find H2S, what can I say? I say to get H2S, I should assume the process is isentropic. For isentropic process, S1 is equal to S2. So since for state 1, I know P1, T1, when I go to the table, I find what is S1. I find H1, which I need, and I find S1. Okay? Once I find S1, I say this is E should be equal to S2S if the process was isentropic. Okay, so since S1 equal S2S is known now, and I know that at the outlet, what is the pressure? I know P2. So now I have two properties at state 2 for the isentropic process. I know S2S, I know P2. What can I get then? I get the value of H2S. And then I can say that H1 minus H2, I can calculate it now because I have the isentropic efficiency. It's equal to the isentropic efficiency of the turbine times H1 minus H2S. And I am done with my first term. I do the same for the second term. I need now to work with my compressor. For my compressor, I know that the efficiency and compressor can be written as H4S minus H3 over H4 real minus H3. Okay, so similarly for state 3, I know T3 and P3. I go to the tables, I get H3 and I get حتى no need for H3, just need S3. Okay, so you get S3. Once you get S3, okay, once you get S3, what do? You go to, you say, I know S3, and this should be equal to S4S. Equals to S4S. Okay, so since I know now S4S and I know P4, I go to the tables. What do I get? I get H4S. Now, I replace in my formula, I know H4S, I know H3, I know the isentropic efficiency of the compressor. What do I get then? I get delta H, H4 minus H3. And in this way, I can find, if you want, the ratio of m dot. This is the technique, okay? So, and in question B, it's much easier. In question B, they told you repeat the question if the efficiencies are 100%. If you have 100% isentropic efficiency, yani the process is isentropic. Yani you don't need to repeat any calculation, and already you computed for case of isentropic scenario, what is delta H? Okay, and in case NT equal NC equal 100, you can directly say, no, I replace H1 minus H2 will be equal to H1s minus H1, sorry, minus H2s. Okay, because the efficiency will be 100%. So I can directly replace delta H by H1 minus H2 by H1 minus H2s, and H3 minus H4 by H3 minus H4s. So let us revise the method together. So first, as we did, we take the whole the whole control volume, because in this way we don't have to go into the work, because the work rejected by the turbine is given to the compressor. So I just have to write some m dot n equals to some m dot n h n equals some m dot out h out, and this will allow me to relate the mass flow rates. Okay, so as we mentioned, if you replace your delta H by their values, you get the following expression for m dot 1 over m dot 14. You need to determine just what is H4s, H2s, and H1, H3. Okay. Now, for the isentropic efficiencies, they are given. So as we did together, okay, first you go to the table. From state 1, you get H1, S1. You say for isentropic case, S2S equal S1. So if you go to tables, you have S2S and you have P2, you will see that you are in the mixed condition, and you get the quality. Once you get the quality, you get the value of H2S. Okay. For air, remember, for air, you have the following technique that you can use, okay, in order to get the temperature T2. And if you want H4S. Remember, whenever you have air and it's ideal gas, what you can use as method, you can use the method of ratio of P. Okay, and you know, the table of air will not give you directly S. Remember, إذا بنرجع على التable of air, you don't have S directly. What do you have? You have S0. Okay, you have H, you have U, and you have PR and VR. Since we don't have directly S for this table, we can do the methods that we learned today. Okay, we say we know the pressure at the inlet and the pressure at the outlet, and it's an isentropic process. When we determine when we want to determine H4S, and we are considering the isentropic process. For the isentropic process, since you are going from state 3 to state 4, okay, you know that from 3 to 4, it's isentropic, so I can write that P4 over P3 equals to P reference, okay, at T4 over P reference at T3. Okay, in this problem, what do you have? You know pressure 3, you know pressure 4. Okay, and you only know T3, but you don't know the value of T4. So what do you do then? You say, I have P4, P3. Let me replace them in my equation. Okay, I have temperature T3. So I go to table of air, and at temperature T3 is known. Since T3 is known, I go to the table of air, I get P reference at T3. Then what is my only unknown in this equation? My only unknown is PR at state T4. Okay, and once I get PR at state T4, I use interpolation in the table to get T4. Okay, now once you have the value of T4, you can get by interpolation what is H4 isentropic. Okay, so keep in mind steam, for steam you have S directly. Okay, and you can find directly then H, while for air to get H4 you don't have directly S from the table. You need to go, because you have only S0, and please never use S0. Okay, as we mentioned, S0 is just to evaluate integral Cp over T. But here we don't need it, integral Cp over T dt. In this case, we don't need this term. We just need H4S. And since the table will not give S directly for us, we need to find H by another method. We need to calculate the value of the temperature based on the ratio, since the table is not giving S directly. Okay, so from this property, we get the value of P reference T4. Then, knowing P reference T4, we determine T4. Once we have T4, what is the second property we have? Okay, and now you have the temperature T4. What is the property that you should find? You should find H4S. So you can go to the table and find. Okay, so remember, please remember that tables of air are not providing directly S. Okay, and to find temperature, I should do it in a different way. نحن بالستيم شو عملنا بالستيم؟ Go back to the given. بالستيم, you have P2, okay, and you say I know that S2S is equal to S1. صار عندي two properties which are needed for steam. Okay, خلص, I am done. I can then find the value I want اللي هي for P2 and S2. I get H2S. While for air, you know that for air, the variable are only function of what? Only function of temperature. But for the exit, we don't know T4, we know only the pressure. So we should say how to get T4 for air, which is treated as ideal gas. We just need to get T4 because we need one property to get what is H4S. Okay, because of this, we should look for T4. And since it's ideal gas and isentropic process, لأنه نحن we are working on getting H4S, we can use then the ratio of pressures. Okay, once you use the ratio of pressures, you can get P reference 4. From P reference 4, you get T4. And from T4, you get H4S, which is the technique we developed in a previous problem. Okay.
دكتور عندي سؤال بس مش بهذا البروبلم، ما في مشكلة؟
ايه اكيد. Yes.
Example 6-8.
Yes. In this before or after this? 6-8 قبل هيدا؟
قبل.
Okay.
ايه مفروض قبل. لحظة بس اشوف لك ايه سلايد.
Yes.
Slide 49.
Slide 49. Just 1 second, I can't see the number of the slide. Yes. Tell me.
دكتور هون جنب على اليمين حاطين نحن بالايكويشن 6.12 تحتها S6 minus S5 equal ل CP واللي هي الباقي. طيب
اوكي.
نحن ليه رجعنا تحت جبنا الاسات الباقي من التيبل بس هون جبناها هيك؟
لأنه أنت عندك heat exchanger. In the heat exchanger, you have two different streams. You have air, okay? And in the cycle, you have R22, okay? أنت for R22, you have the tables of R22. you use them. While for air, you can treat it as ideal gas, so you can use other relations. عرفت كيف؟ All the relations that they used between 5 and 6 are only valid for ideal gas case. And since you have air, and you can treat it as, they told you, you can treat it as ideal gas, you can use directly the formulas of delta S for an ideal gas. While for R22, you need the tables to get S at different points and do delta S. اوكي هيدا الفرق.
دكتور بس كمان انه S6 و S5 بنجيبهم من التيبل، اذا بنعملهم ماينس بعض بيطلع نفس الجواب. بهيك حالة مثلا انت عم تقولي هيك
لا
صح.
ما انت انا اللي عم اقول لك هي، انت بدك تنتبه، الاير ما عنده اس، بيعطوك اس زيرو. في فرق بين اس واس زيرو. اوكي يعني ما فيك تستعمل، ما عندك اس للاير. you don't have s for air directly. اذا بدك تستعمل الاس زيرو شو فيك تكتب؟ فيك تكتب اس 6 minus اس 5. هلا هون ثاقبت انه نفس البريشر. ايه اذا بريشر كونستنت بتزبط، لانه هيدا الترم بيروح تطلع equal ل اس 6 0 minus اس 5 0. بس if you don't have constant pressure ما بتزبط، بصير بدك تجيب اس 06 واس 05 ترجع تعمل minus r ln P6 over P5.
اوكي دكتور ميرسي.
اوكي so هلا تقريبا خلصنا. اوكي هلا في a small section that I will explain for you، بس هي يعني it's a continuation of before، ما في شيء جديد إذا بدكم. Okay, so here we'll do some particular cases of heat transfer of work in internally reversible steady state flow processes. So if we take, for example, a certain device عنده just one inlet, one outlet, and it's exchanging both heat and work with the surrounding. You know that if you write the energy balance شو بيطلع لنا؟ عندنا Q dot minus W dot plus M dot H1 minus M dot H2 equals 0. Okay, now if we want to consider انه عندي reversible, if I have a process from 1 to 2, a reversible process, how can I compute integral Q dot? نحن بنعرف انه for reversible process Q dot over M dot is integral from 1 to 2 of TDS. يعني إذا بتتذكروا بالصف شو قلنا؟ فينا for a reversible process to compute Q dot over M dot as the area under TS graph. Okay? And if we replace this بالequation of energy balance اللي هي W هون إذا بدكم they just took W dot to the other side، لأنه وقتها كانت هون شو كانت؟ minus W dot over M dot. So they took it to the other side. Neglecting variation in kinetic and potential energies, these two terms will cancel out. فبيضل عنا W dot over M dot is equal to integral from 1 to 2 TDS. Okay, لأنه هيدي اجت محل شو؟ محل Q dot over M dot. For reversible process, you can replace Q dot over M dot by integral TDS. And we already know from previous analysis, what is TDS? You can replace TDS by DH minus VDP. Okay, if you replace TDS by DH minus VDP in this equation, what do you get? You get the following. You get, instead of integral TDS, I will see integral DH from 1 to 2 is H2 minus H1. And integral VDP from 1 to 2 will give you minus integral 1 to 2 of VDP. So if we replace this with formula of work, and here let us go back to this formula. Replace integral TDS by its value. شو بتطلع integral TDS? Integral قلنا of DH. Okay. So we replace this term by H2 minus H1. لأنه integral of DH is H2 minus H1. Minus integral VDP between 1 and 2. Now, H2 و H1 will cancel out لأنه عنا plus H2 minus H2 وعنا plus H1 minus H1. So what do we deduce? إنه for a reversible case, how we can write the work for open systems? For open systems, W dot over M dot for an internally reversible process is minus integral from 1 to 2 VDP. Okay, ونحن عادة in majority of application بناخد let's say liquids. If you have liquids, for liquids the specific volume is nearly constant. So whenever you have a liquid, you can treat the specific volume as constant. ساعتها فينا نطلعه لبرا الانتجرال. Okay, وبيصير عنا إنه W dot over M dot is minus V delta P. So in case you have a liquid, okay, and you have an internally reversible process, you have the right to say that W dot over M dot for internally reversible is minus V delta P. Okay. هلا نحن will not go through further chapters, بس إن لو عندكم chapter 8 كنتوا بتعوزوها كتير لها. يعني أنتوا just you should know this. إنه if I have a reversible process and it's a liquid, I can replace W dot over M dot by minus V delta P. اوكي
دكتور إذا ما كانت ليكويد نرجع نستعمل اللي شفناها بالصف إنه
إذا ما
integral
كانت
PdV.
liquid إذا ما كانت liquid شو بنعمل؟ بدنا نعرف V function of P. يعني مثلا هلا بنشوفها بنكست سلايد. يعني أنا إذا بقول لكم إنه عندي process polytropic، أوكي؟ أنتوا بتعرفوا إنه for polytropic process شو relation بين V و P؟ V P to the power n equal constant. Sorry, Vn to the power. يعني هون شو الفكرة؟ إنه أنا I can replace V by what? V هي 1 over هون V to the power n times P. V to the power n times P equal constant. يعني لما يكون polytropic process, you can replace V by constant over P to the power 1 over n. اوكي ساعتها بتعملوا انتجرال. يعني بتتذكروا هولي من chapter 3 if you remember them. إذا كان polytropic process PVN equal constant، إذا كان عنا n equal 1، اوكي بتصير V times P equal constant. اوكي so هون just you replace specific volume by its function and you integrate. لكم حق انتم دغري تستعملوا الفاينل results هولي. اوكي you have the مثل بالchapter 3 you have the right to use them directly. okay that's it. يعني هيدا chapter ما بقى في شيء. so just if you have polytropic or n equal 1 وأنا أنتم ما لازم تحفظوا شيء. you just do the integral. يعني you just replace and integrate the function, you get the result. okay this is chapter 6. if you have any question فينا نرجع إذا بدكم نرجع نعمل review session whenever you want. just tell me, you can send me an email what time is fine for you, and if you have questions